the resolved shear stress, and the resolved shear stress is basically the value which is dependent upon the normal stress or the tensile stress, and it is dependent upon the angle of the slip direction and slip plane with regards to this plane on which tensile force is being applied. Clear?
Yes, sir.
All right. Now let's look at the Schmidt's law. It says that it is found that the value of TR, the resolved shear stress, at which slip occurs in a single crystal with specified dislocation, density, and purity. Let's leave it for the moment. We'll try to understand it later on, but with these two constants, the resolved shear stress has a value which is known as critically resolved shear stress, TCRSS. A single crystal having a specific dislocation density and purity would have a critical value of resolved shear stress which is constant. And how do we define it? We say that cos phi cos lambda is the Schmidt factor, and the tensile stress at which the crystal start to slip is known as the yield stress. So if you are doing a tensile test experiment and you're applying this tensile stress, you have a tensile stress strain curve. There would be a value of yield stress. This is the value at which plastic deformation actually starts. So for the critically resolved shear stress, you have this value at which the plastic deformation start. This multiplied by the maximum value of the factor, Schmidt factor, would give you the critically resolved shear stress value. All right. So if you look at this term mathematically, you would have the maximum value of this factor at 45 degrees centigrade when the plane and the direction they are at 45 degrees from the normal. You would have the maximum value of this factor. This factor multiplied by the yield stress of the material would give you the critically resolved shear stress value for the single crystal. In other words, in a given system, there may be many available slip systems, like you had 12 slip systems for FCC. That means 4 different planes and 3 different directions, with each plane are the slip systems for FCC. As the load is increased, the resolved shear stress on each system would increase, and eventually the resolved shear stress would reach the critical resolved value, maybe on one of the system. So the earliest the critical the resolved value increases or goes beyond the critical resolved shear stress on any one of the slip system, this would be the primary slip system. The stress required to cause slip on the primary system is the yield stress of the single crystal. Obviously, you know that. And as the load is further increased, the critical resolved shear stress value may be reached on the other systems. So the condition for for the plastic deformation is that the resolved shear stress value should be greater than the critical resolved shear stress value. Is this point clear to you guys? G.
Yes, sir.
Any doubt? All right. So from the Schmidt's law, it is apparent that the primary slip system will be the system which will have the greatest Schmidt factor. All right. It is not necessary that your plane and direction, slip plane and direction are at 45 degrees. All right. But the one which would be closest to this factor, the slip plane and direction that would be closest to this factor, that would be your primary slip system. Is this point clear?
Yes, sir.
All right. So if we have a single crystal and we know that the critical result shear stress value is 3000 psi for the single crystal. The slip direction is at 35 degrees and the slip plane is at 60 degrees to this force that is being applied. The force that is being applied, or the normal stress that is being applied onto the material, is 65,000 psi. Now the first question is, will this single crystal yield or go into plastic deformation? G, can you solve it out? Your stress is 65,000 psi. The two angles are given to you. You just have to plug in the value and you see that your resolved stress comes out to be less than the critical resolved shear stress, which is 3000 psi. So what do you think? Will the single crystal yield or go under plastic deformation?
नो सर, क्योंकि वैल्यू उसकी सर उससे कम है।
जी बिल्कुल। तो जो shear stress resolve होके इस direction में act कर रहा है on this plane, the resolved shear stress value is less than the critically resolved shear stress value. So the crystal or single crystal will not undergo the plastic deformation. If not, then what is the stress required? How can I find out the stress required to cause this deformation in the material? What is the value of this stress, the normal stress, which will cause the plastic deformation in the material?
सर इंक्रीज होगी सर इसकी वैल्यू ताकि हमारे पास टोटल 3000 आ जाए।
इंक्रीज तो होगी, लेकिन कितनी होनी चाहिए? जी
सर एंगल से भी फर्क पड़ेगा।
जी सॉरी,
तो 3000 से माइनस करेंगे तो
3000 से माइनस
जो वैल्यू आएगी वो उतनी इंक्रीज करनी पड़ेगी।
no, what actually, what stress is necessary? जी जी,
सर इसमें हम 3000 के इक्वल रख के क्या कहते हैं फाइंड कर लेंगे,
वेरी गुड,
मतलब उससे ग्रेटर होना चाहिए।
वेरी गुड. So your critical resolved shear stress would be equal to or greater, it should be equal to 3000 psi. That means the normal stress corresponding to this critical shear stress is something that you should have to have the plastic deformation. So your normal stress or the yield stress should be such that it corresponds to the critical resolved shear stress value in order to cause the plastic deformation. So for deformation to occur, the applied stress must be greater than or equal to the yield stress of 7325 psi. Is this clear?
सर रिपीट कर।
Who is this?
सर वो मेरा नेटवर्क इशू आ गया था बीच में तो।
अच्छा अच्छा, ठीक हो गया. I'll repeat it, but let's first try to understand the problem. मैं ये पूछ रहा हूँ कि if this much normal stress is not causing the deformation in the material, how would you find out the stress that would cause deformation in the material? कैसे find out करेंगे? Can you hear me?
यस सर
Yes,
सर
sir.
3000 के इक्वल करेंगे
जी
रिजॉल्व स्ट्रेस को, फिर वहाँ पे वैल्यूज पुट करेंगे जो लेमडा की और फाई की हैं, और उससे
बिल्कुल
निकाल।
बिल्कुल. So this is the critical resolve value. For this critical resolve value, you already know the value of lambda and phi. तो इस डायरेक्शन और इस प्लेन के एंगल के लिए द स्ट्रेस दैट इज रिक्वायर्ड, you will find out that stress. That stress comes out to be 7325 psi. So if you apply a normal stress of 7325 psi for a plane at this angle and the direction which is given to you, you would have the resolved value, shear stress value of 3000 psi. And you already know that 3000 psi is the critically resolved shear stress value. That means if you have this stress, there would be the deformation that would be taking place in the material. So any stress value which is greater than this 7325 psi or equal to this would essentially result in the deformation of the within the material. Clear enough?
यस सर क्लियर।
Yes, sir.
So far we had looked into a single crystal. हमने ये बात की थी कि we are applying the stress on a single crystal जिसमें एक ही orientation है. अगर मैं कहूँ, if I say that this plane which is let's say यही एंगल ले लें, lambda is let's say 30 or phi is let's say 45. Phi is the angle of the plane with respect to this normal. तो ये plane जो है ये इस ओरिएंटेशन पे पड़े हुए हैं 45 डिग्रीज की. ऑलराइट, इज दिस
यस
क्लियर?
Correct, sir.
अच्छा, लेकिन इफ वी हैव अ पॉलीक्रिस्टलाइन मटेरियल जिसमें एक ग्रेन ऐसे पड़ा हुआ है, एक ग्रेन ऐसे पड़ा हुआ है और ये तीन ग्रेन है, हो सकता है इस ग्रेन में 45 के प्लेन्स ऐसे हो, इस ग्रेन के अंदर 45 डिग्री के प्लेन्स ऐसे पड़े हुए हो और इस क्रिस्टल के अंदर 45 के प्लेन्स ऐसे पड़े हुए हो. ऑलराइट, इज दिस क्लियर टू यू गाइस?
Yes, sir.
Yes, sir.
यस
So the phi angle which is 45, it would change with regards to the orientation of the grain. I just want to make this point clear. I hope that this point gets very clear to you guys. Is it clear or is there any confusion in this point?
Clear, sir.
All
क्लियर
right.
सर।
Now it says slip planes and direction change from one crystal to another. That means although the value of critical resolved shear stress would be 30 and 45 for lambda, but this 30 and 45 would be changing from one crystal to another. So if you have this as one grain, इसमें ये एंगल हो सकता है, but if for another grain the angle might be this or the angle might be this. Similarly, in some another grain, the angle might be different than this angle in this grain. So the resolved shear stress would vary from one crystal to another. Although you know that these two would give you the maximum value, but for every crystal the resolved shear stress would vary because the angle of slip plane and slip direction and slip plane would be varying with regards to the normal force. The crystal with the largest resolved stress would yield first and the other crystals would follow. Is this point clear to you guys?
Yes, sir.
All right. Now we'll move towards the strengthening mechanisms, and would like to see how the strengthening mechanisms work in materials. There are essentially four strengthening mechanisms that we are interested in: the grain boundary strengthening mechanism, solid solution strengthening, dispersion strengthening, and strain hardening. So let's first look into the grain boundary strengthening mechanism. It says that a polycrystalline specimen, if the stress is being applied onto a polycrystalline specimen, deformation in each grain is different. Why is it different?
सर बिकॉज एंगल सर हर एक में सर डिफरेंट हो जाएगा,
Very good.
ओरिएंटेशन भी चेंज हो जाएगी सर.
Very good. So deformation in each grain is different due to difference in orientation with respect to the applied stress. इसका मतलब क्या होगा कि लेट्स से अगर deformation हो रही है तो this grain, it might move more in this direction. इसमें अगर शेयर हो या let's say ये deformation की direction है, let's say I am assuming this is the direction. तो ये जो क्रिस्टल है ये ज्यादा मूव कर रहा है इस डायरेक्शन में, तो ये वाली ग्रेन बाउंड्री जो है इट इज मूविंग मोर और ओवरलैपिंग द अदर ग्रेन, और यहाँ पे डेफॉर्मेशन कम है तो ये वाली ग्रेन बाउंड्री इस डायरेक्शन में कम मूव हुई है. इन अदर वर्ड्स, ड्यू टू द applied shear stress, this grain boundary has moved more in this direction, whereas this grain boundary would move lesser in this direction. Is this clear?
Yes sir.
Yes, sir.
All right. Now, neighboring grains tend to maintain continuity at the grain boundaries and remain intact. ऐसा नहीं हो सकता कि यहाँ पे अगर ये ज्यादा मूव कर गया और ये कम मूव किया तो देयर शुड बी एन एयर गैप. These grains would try to keep intact with each other, and in order to do so they create strain at grain boundaries. ये इसको पकड़ के रखेगा और उसकी वजह से एक खिंचाव पैदा हो जाएगा इस जगह पे. Clear?
Yes sir.
Yes, sir.
All right. Now, strain near the grain boundaries differs markedly than the strain at the center of the grain. Since यहाँ पे एक दूसरे को पकड़ के रखना है, ये ग्रेन बाउंड्रीज पे एक दूसरे को पकड़ के रखना है, तो the strain at the grain boundaries would be sufficiently high as compared to the strain that would be there within the center of the grain. Does this point make sense?
Yes, sir.
All right. Once you know that there is strain that exists at the grain boundaries which is different than the grain itself. तो grain boundaries के ऊपर एक खिंचाव पैदा होगा that would be higher as compared to the strain at the center of the grain. Now, plastic deformation क्या है? Plastic deformation is basically the movement of dislocation. The dislocations move along slip planes till they reach the grain boundaries. You already know plastic deformation को हमने define किस तरह किया था? हमने define किया था it is movement of dislocations, and dislocations move along specific slip planes along specific slip directions. So dislocations move along slip planes till they reach the grain boundaries, and they face difficulty to cross grain boundaries due to number one, change in crystal orientation, and number two, strain near grain boundaries. So पहली रीजन क्या है कि ये एक स्लिप प्लेन है जिसके ऊपर डिस्लोकेशन मूव कर रही है इस डायरेक्शन के अंदर. Now as it reaches the grain boundaries, यही स्लिप प्लेन और डायरेक्शन जो है ये ओरिएंटेशन की वजह से यहाँ पे मूव हो गए. So this grain boundary is basically resisting the motion of dislocation due to the change in orientation. इस dislocation को अपनी orientation ऐसे करने के लिए energy चाहिए, and that resistance is caused by the grain boundary. So therefore, the grain boundary is making the dislocation motion difficult due to the change in crystal orientation. Is this point clear?
Yes,
Yes,
sir.
sir. Yes, sir.
All right. So हमने डिफाइन ये किया कि प्लास्टिक डेफॉर्मेशन होगी तब जब डिसलोकेशन मूव करेंगी, और डिसलोकेशन जब मूव कर रही होंगी फ्रॉम वन ग्रेन टू अनदर, ओरिएंटेशन का डिफरेंस जो है दैट वुड क्रिएट डिफिकल्टी इन द मोशन ऑफ डिसलोकेशन मूवमेंट. सेकेंडली, द स्ट्रेन नियर द ग्रेन बाउंड्रीज. Grain boundary is disordered and not easy for dislocation to move as it is in the grain. हमने पहले ही कहा था कि ग्रेन बाउंड्री पे खिंचाव मौजूद होगा, तो डिसलोकेशन वुड स्टार्ट टू पाइल अप एट द ग्रेन बाउंड्री. ये एक डिसलोकेशन आई यहाँ पे आके जमा हो गई. सो व्हाट इज एसेंशियली हैपनिंग इज कि डिसलोकेशन यहाँ पे आके जमा होना शुरू हो गई. Neighboring grain tend to create strain at the grain boundaries to maintain continuity at grain boundaries and remain intact. ये हमने पहले ही देख लिया. तो उसकी वजह से होता क्या है कि pile up of dislocation start to take place, which creates strain in the neighboring grains, and this is basically a strengthening mechanism. कि डिसलोकेशन मोशन इस वजह से मुश्किल हो जाती है कि dislocation starts to pile up at the grain boundaries and create further strain, which makes dislocation motion further more difficult. Clear?
Yes, sir.
All right. So हमने ये देख लिया कि ग्रेन बाउंड्री की मौजूदगी जो है वो डिसलोकेशन मोशन को मुश्किल बनाती है, और डिसलोकेशन मोशन मुश्किल होगी तो प्लास्टिक डेफॉर्मेशन मुश्किल होगी. Now, if we say कि we have two sort of grains. One is these fine grains, the other is this relatively large in size grains. तो अगर हमने मटेरियल की स्ट्रेंथ इंक्रीज करनी है, स्ट्रेंथ इंक्रीज करने के लिए which of the two grains should we go for?
Sir, fine grains.
All right, one answer is fine, the other is this coarse grain, the bigger one. Anybody who has a difference in opinion? किसी को ये लगता हो कि we should go for coarse grain instead of the fine grain to increase the strength of the material? किसी को भी नहीं लगता? ऑलराइट, जिनको ये लगता है कि वी शुड गो फॉर फाइन ग्रेन, हाउ मेनी ऑफ यू थिंक
Sir.
दैट वी? जी, ऑलराइट, फाइन ग्रेन की जो जो दोज हु आर इन द फेवर ऑफ फाइन ग्रेन्स फॉर इम्प्रूवमेंट एंड स्ट्रेंथ, कैन यू गिव मी अ रीजन फॉर दैट?
तो सर क्योंकि जो सिंगल का होगा स्ट्रांगनेस वो उन फाइंस में सब में होगी, तो सर वो आई थिंक सो ज्यादा स्ट्रांग होगा, ज्यादा स्ट्रेंथन होगा।
सिंगल का होगा क्या मतलब, सॉरी?
सर सिंगल का एज कंपेयर टू जो फाइन है उसका कम होगा ना, क्योंकि उसमें सर मोर देन वन है और उनके आपस में कोलैबोरेशन होगी।
ऑलराइट, वी ग्रेन बाउंड्री किस में ज्यादा है, फाइन में ज्यादा है या कोर्स में ज्यादा है?
सर फाइन में।
ऑलराइट, देखिए अगर एक
यस सर फाइन में।
डिसलोकेशन, इफ अ डिसलोकेशन इज ओवर हियर एंड इट हैज टू गेट टू दिस पॉइंट, तो अगर, तो ये बड़ी एक बड़ा ग्रेन है, कोर्स है, तो दिस इज द डिस्टेंस इट हैज टू फेस बिफोर इट फेसेस अ डिफिकल्टी इन मोशन व्हिच इज दिस ग्रेन बाउंड्री। लेकिन अगर मैं यहाँ पे छोटे छोटे 4 ग्रेन बना दूं, तो इट हैज टू फेस दिस बैरियर, this barrier, this barrier, and ultimately this barrier. So the more the number of grain boundaries, the higher would be the barriers in the motion of dislocation. That means the more difficult it would be for the dislocation to move. And if the dislocation motion becomes difficult, the strength of the material or plastic deformation would become difficult, and the strength of the material would essentially increase. Is this clear, or does this make sense to you guys?
यस सर क्लियर है।
All right. So fine grains, more barriers to dislocation. Stress has to be increased to push dislocation against the pileup into the adjacent grains, resulting in the strengthening effect. Now, this is the Hall-Patch equation, which relates the yield strength of the material to the grain size, which is under root inverse under root of the grain size. So the smaller the grain size, the higher would be the yield strength of the material. This is also known as grain size refinement process. So normally in material science, if you have to increase the strength of the material, one of the option is to increase refine the grain size. And this grain size refinement is normally performed by thermomechanical treatments or heat treatments or microalloying, that you could apply thermal and mechanical energy at the in a process to reduce the grain size. You could just do the heat treatment, I mean by heating up the material and cooling it in a certain way to refine the grain size, or you could add micro alloying elements that basically control the grain size of the material. Uh, Grain size could vary from 1 micrometer to 1 millimeter in aerospace alloys, resulting in difference in strengths that could be achieved. So this is one of the strengthening mechanism uh, that is being utilized in material science. The other is the solid solution strengthening. It says in substitutional solid solution, on the lattice site of a host atom, an atom replaces a host atom. This is the solid solution. You already know that. Solute is slightly bigger or slightly smaller than the host atoms. One atom is replaced. See the distortion it creates in the lattice. The general lattice is distorted up to many atomic distances. So you can have a smaller atom replacing the host atom, or you could have a bigger atom replacing the host atom, and as a result you would see that there is distortion or stress is created within the lattice. And it is, if there is a dislocation over here, it is this stress that is being created which creates difficulty in the dislocation movement along the distorted planes. So due to the addition of element which substitutes the host atom, you essentially have a stress that is being created, and this stress basically resists the motion of the dislocation, uh, which is again a resistance for the plastic deformation. For example, addition of nickel and copper. Nickel and copper are substitutional solid solutions, and we see that the tensile strength and the yield strength of the material increases as the weight percent of nickel is increasing in the material. So as you have more amounts of nickel added, the amount of distortion increases, which increase the tensile strength or the yield strength of the material, or it basically increases the resistance of the material against plastic deformation. The empirical relationship is that the yield strength is approximately equal to the under root of the concentration of uh, the foreign atom that is being added to the material. The reason for increase is that impurities or the alloying elements, they increase the critical resolved shear stress value. So the critical resolved shear stress values increase, and this basically increases the resistance to the slip, thereby making plastic deformation difficult. The other is the interstitial solid solution. That means an interstitial atom occupies the interstitial space. If you see the strained lattice, interstitial atoms are 50 to 80% smaller than the host atoms or the solvent atoms, and they are slightly bigger than the interstitial sites. They push neighboring atoms and create stress around. Field spreads over an area many times bigger than the atom itself. The important thing is the distortion created by interstitial atom is much more than the substitutional atom, although interstitial atoms are much smaller in size. Think about it, that why is it so? Why is it the interstitial atom, it creates more distortion as compared to the substitutional atom? Just to give you an example, effect of alloying elements on steel at room temperature. Forget ferrite at the moment, just think you're talking about steel. So carbon and nickel or phosphorus, which form interstitial solid solution, they create only a small amount of them create a large improvement in yield strength, whereas copper, manganese, molybdenum, nickel, which form substitutional solid solution, large amount of these create lesser effect on yield strength. So did you notice the effect that carbon and nickel is much more than molybdenum and nickel, and you need to think about it. Why is it so that substitutional solid solution creates lesser effect as compared to interstitial solid solutions on the yield strength of the material? All right.
Yes, sir.
So